let's see. Last time I was reminding you or telling you about this older history of Conway. And let's play with that a little bit because it's very interesting and it relates to what we were already doing with the Alexander polynomial, and then we'll go back to the bracket and things. But what John Conway did was, he said in a paper around, the paper was written circa 1969, but I think people didn't really appreciate it very much until later when he started talking about it again. But these are axioms, okay? They're axioms for an invariant. So given K an oriented thing. Okay. Axiom number one, there is an nabla K of Z belonging to the ring of integer polynomials in Z. And if K is equivalent to K prime, then nabla K of Z is equal to nabla K prime of Z. Okay? So that's sharper than Alexander polynomial because Alexander polynomial was equal dot, remember, where there was some power of T. We were looking at that before. And then the second axiom is that this way, I'll write it symbolically and then say what I mean by it. And I think I'll put into my first axiom and the unknown. We have to put it somewhere, so let's put it there. Okay. So you have a polynomial, and on the unknown, it's equal to 1. And then this axiom, that's the whole system of axioms. And this means that nabla K plus minus nabla K minus is equal to C nabla K naught, where K plus, K minus, and K naught are diagrams differing only as shown. Okay, so those are our axioms. So you could have 3 diagrams and they differ only as they're shown there. There's some crossing in this diagram, the K plus with a plus. And if you switch it, that's the K minus. You don't do anything else to the diagram, or you smooth it like that, and you don't do anything else to the diagram. And that triple of knots and links has a relationship among the polynomials like that. So it's similar to what we were doing with bracket, where bracket has an even simpler kind of relation, right? And then there is a theorem that if delta K of T is the Alexander polynomial, then the Alexander polynomial of the knot or link is equal dot to nabla for Z equal to root T minus 1 over root T. I'm going to illustrate the theorem. Prove it. We don't have time to do more stuff about things about Alexander polynomial. It's interesting to see how to prove that, of course. So let's do an example. Well, the very first thing you want to do is to do some very simple things, simple calculations with this. So let's see what would happen. I can write down the relation and then close this up in some way, and I get a specific relation. Okay. So I wrote down the general relation, And then I think, let's see, I could close it in an oriented way like that. And then these are equivalent. So that means that this is zero. This is a Z. So I just got that zero, which I'll write with a slash through it, is equal to Z times non-law of, I'll link the two components. If that's true, we can cancel the Z. That can't make any difference if that polynomial ring. Z times something is zero, then that thing is zero. There are no zero divisors there. So zero is equal to non-law of 2. So now we know one extra fact. We know that non-law of single loop is 1 and non-law of 2 loops is 0. Okay, and I could generalize this. I could put a black box in here. I could put a black box in there. Put a black box in there. I could put a black box in there, and one here, and one here. Or that means anything, a 1-1 tangle, whatever I like. But this is still equivalent. This is still ambient isotopic. You just twist it around in space, right? And according to Reitemeister's theorem, that's the same, can be done by Reitemeister. So this will still be 0. And so we get that non-law of K1 disjoint union K2 is equal to 0. Disjoint union. And K1 and K2 are both non-empty. So if you have a link that somehow turns into, by isotopy, turns into 2 different components, they could be knotted, whatever, linked, but they're completely disjoint from one another, contained in 2 separate 3-dimensional balls, then the Conway polynomial will be 0. That's also true of the Alexander polynomial. So we have that, and now let me see. We ought to try something a little harder. What will happen if I take the Hopf link here? Of course I want the Trefon now to handle destroying the Trefon now. If I wanted Hopf link, here's the Hopf link. Okay. Hopf link. And we have non-law of the Hopf link minus non-law of, now that's a negative crossing. I kind of wanted a positive crossing, so I'm just going to switch somebody. Just felt like I wanted a positive crossing. So we'll orient that one that way. Okay. And then this crossing here is a positive crossing, and I can switch it. So then I would have entirely over and entirely under. And that goes that way, and that goes that way. And this is going to be equal to Z times non-law of, I'm smoothing it this way, right? The arrow direction. Okay. So I looked at that and I realized, well, that's good. I know everything except the Hopf link, which is my unknown. This is 0. And this guy here is 1. So this implies that the polynomial for the Hopf link, positive Hopf link, is equal to and if I were to take the mirror image of that, I would call that the positive Hopf link. If I took the mirror image of it, or I reversed one of these crossings, and maybe I'll just reverse it. Let's just do that. I'll just put that in the opposite direction. leave this one alone. Now all the crossings are negative, all that H minus, and we'll get that that's minus C. I'll leave it to you to check. With our calculation, we'll just go through, but it'll flip the sign. So actually, and that would happen if I took the direct mirror image as well. The direct mirror image will look like this. And they aren't really the same as reversing one of the crossing directions. Try that for yourself. I'm leaving this one, but the orientation's the same. And so this is HK, H plus star. But H plus star exercise is equivalent to H minus. There's the exercise rounded that. But here's H star, and nabla H star will also be minus E. So it does detect a little bit about mirror images and links. You will see some detection of mirror images for links with this invariant. But now we know the off link, and now we're in a position to see what we can see about the trephine knot. So here's a positive trephine knot. And I can switch that crossing right there. And it becomes unknotted, of course, that's good. And then that's equal to Z times the result of smoothing crossing. And as you see, I get a positive uplink. Okay, so that says that nabla trefoil minus 1 is equal to Z times Z, that being the value of the positive uplink. And so we know that the trefoil knot in Conway's axiomatics is 1 plus C squared. And now we can illustrate the Conway theorem. Because what if I were to take 1 plus root T minus 1 over root T and square it? Then I get 1 plus T inverse minus 2, which is equal to T minus 1 plus T inverse, which is equal to T squared minus T plus 1, which is our previous calculation of the Alexander polynomial of the trefoil knot. So that's showing you that Conway's theorem at least works for the trefoil, but it works for everything. So this is rather amazing if you think about it, because remember what we had to do in principle to get the Alexander polynomial. We start with presentation of the fundamental group. We then write it out in the Alexander Quandl form. So we use TA plus 1 minus TB at every crossing, and we get a matrix like a generalized coloring matrix, and then we have to take the determinant of that generalized coloring matrix, and that gives us the generalized modulus that is the Alexander polynomial. So it involves a lot of matrix algebra, determinants, and so on, and you can prove theorems about the Alexander polynomial by using that definition for sure, and that's similar to what Alexander did originally, but it uses a lot of linear algebra at its base. And this is using nothing but combinatorics of the diagrams. There's no matrix algebra, nothing. This will always work. This axiom, these axioms will always bottom out and compute something. That's what I mean by saying that they work. So let's look at the axioms. Putting a circle around them so they don't get confused with the calculations around them. But they're very simple axioms, right? There's a polynomial, and it's normalized to be equal to 1, and it satisfies that relation. So in order to see that the calculation will bottom out, you need to know that you could always end up with nothing after a while, but polynomial. So something has to be getting simpler. This is getting simpler. It's got one fewer crossing. And one of these could be simpler if you choose it right because of a fact that we mentioned before. Let me illustrate it in another color. It was a fact that looked like it was just about Googling diagrams, but it's a key fact. If I draw a diagram like this, always crossing under before I cross over, then it's unknotted. That was what we observed before. But that means that if you have some knot and you want to do a calculation like this, you could decide on how to unknot your knot. You could choose a set of crossings that would unknot your knot. And one way to do it is to draw your knot diagram, and then next to it, draw another copy where you went under before you went over. And then look between them, and there will be some crossings that are different. And you know that if you switched all of them, it would be unknotted. So then you label them. I'm just telling you how to compute. You label those crossings, and you say, okay, that's the one I'm going to work on. I'm going to have one of these be the switched crossing that is closer to an unknot. And then I get that the original diagram is equal to the simpler diagram, one switch closer to the unknot, plus something with a smoothing. Then I work on this diagram and find the other, and the next crossing that will simplify that. Of course, it could be plus or minus, because this equation can be thought of either as this guy is equal to that guy plus z times this guy, or this guy is equal to that guy minus z times this guy, either way, right? So you can compute by making it simpler by aiming toward a specific unknot. And you can tell a computer to do that too. And so this will bottom out. So one, the axioms bottom out. I won't write it. And two, and this is harder, they won't give you any contradictions. That is, you could imagine there are a lot of different pathways down to compute the end. Couldn't you get different results? But the answer is no, you can't. You get a unique result out of this, but the proof that you get a unique result out of this algorithm is more complicated than the proof that you get a unique result out of the bracket, right? We proved yesterday, or Friday, that the bracket, or Monday, we proved Monday that the bracket gave a unique result. And why? Well, because we have the state sum formula for the bracket, and that's well defined and it satisfies the bracket axioms. Here, you can do that too. You can find a certain kind of state sum for this, which satisfies this formula, and then you know that it works. Or you can prove by induction, careful induction on diagrams, that it will always give you a unique answer. Okay, so that's the Conway polynomial. If you're interested in playing around with Alexander from before, then I recommend compute Alexander this way, compute Alexander that way, compare the results and see if you can get the same result. And that's quite interesting because you may have already sat down and done Alexander, say, for the figure 8 knot, right? That was one of our suggested exercises. You could do it by looking at the fundamental group of the figure 8 knot and we're writing out the modulus of all that. But to do this for the figure 8 knot, well, gosh, that's going to be very easy, and I won't do it, but I recommend it. I won't do it today. So here's a figure 8 knot, right? And we were doing the figure 8 knot for the bracket, and strategy is very similar. If you went up here to this crossing, it's positive. If you switch it, you'll get an unknot. If you smooth it, you get a half length. So it's almost the same as doing the trefoil. But this half length, what's the difference going to be? Are you going to get the same result or a different result? Maybe we ought to actually do the figure 8 knot just to compare. Remember that Conway gives us 1 plus c squared for this one. And let's spend a moment. Oh, where's my plus? Oh, it's up here, sorry. Yeah. So let's do Conway for the figure 8 knot, just for reference and for practice. So we saw this before. There are 2 plus crossings and 2 minus crossings in the figure 8 knot. We know it's equivalent to its mirror image and other things. So here, we're doing Conway though. So here, I'm going to switch that crossing. Plus minus, sorry. Like that is equal to z times result of smoothing it. Okay. So this is equivalent to an unknot. So this is going to give me a 1. Now what about this? Oh, this is H minus, not H plus. That's interesting, right? When you decompose the trefoil knot, you got an H plus. When you decompose the figure 8 knot, you got an H minus. And that's going to have a minus. And so that implies that the figure 8 knot is equal to 1 minus c squared. We have that the trefoil knot is 1 plus c squared. So indeed, we are distinguishing between the figure 8 knot and the trefoil knot with Conway polynomial. And what about Alexander? Well, Alexander in T is equal dot using the theorem to this evaluated for z equal to root t minus 1 over root t. And so I'm going to get 1 minus root t minus 1 over root t quantity squared, which is equal to 1 minus t minus 2 plus t inverse. I get there. And so I get 3. I get 3 minus t inverse, which could be written as equals dot squared minus 3 plus 1, right? I multiply by t and minus 1, and 3t. Multiply by t and change the sign. And that's the way I have often bumped into it when I calculated it the other way. And for example, if you take t equal to minus 1, then you get 1, 3, 1, 5. E mod 5z was the coloring number for the figure 8 knot. Okay. So there you are. That's doing the exercise the easy way. If you want to do it from the fundamental group of the figure 8 knot, you'll have a more complicated calculation, and you should, after some care, end up with that polynomial out the end. Let's see how much time we have, because I had in mind possibly tell you, yeah, let's spend a little more time on Alexander now. I said that Alexander had a state sum, and I'm going to show you the state sum. Big sum for both Alexander and Conway. And this goes back to Alexander's part one of this, Alexander's original definition. This is very interesting. This is, you could have some fun looking at this paper from 1928 by Alexander in Transactions. Here's what he did. He said, I'm going to look at a knot diagram. It was a combinatorial algorithm. I'm going to look at an undercrossing line. I don't care whether this overcrossing line goes left or right in this notation. And I'm going to put two dots on the left of the undercrossing line. And then I'm going to have the regions labeled. Are labels for region. Okay. And then there's going to be a module generated by the regions. And one relation at each crossing. And the relation is TA minus TB plus D minus D. And then you make a matrix of regions versus crossings, and you take a certain determinant from the matrix that you get. And that will be the Alexander polynomial. So in order to illustrate that, I'm just going to do it on the trefoil knot and see how this works. So suppose we have a trefoil knot. And dots on the undercrossing. And we can label the region. So I'm going to write down this relational information in a matrix. Crossing, one crossing, and two crossing. So this is crossing number one, this is crossing number two, and this is crossing number three. So we can just read this off, right? We have TA minus TB plus D minus T. We have, that's for one. For two, we have TA minus TC. Plus D minus E. For crossing number three, I have TA minus TE plus D minus B. And if you examine this carefully, you will see that it is well, it's not square, of course. Maybe I should just tell you the algorithm rather than talking about what you might see. What you do to get the algorithm is you take all but two of the regions, and then you end up with a square matrix because there are two more regions than there are crossings in the diagram, right? In the diagram. So this is a square matrix, and we'll call this matrix M. And then you take the Alexander polynomial is equal to the determinant of that matrix. Now, what do I eliminate? A and B are adjacent regions. That is Alexander's original definition of its polynomial. Now, you can have lots of questions here, like where did you get that? Main question, right? How did you think of that? But before we say anything about that, let's calculate this determinant. I hope I didn't make any mistakes in writing it out. Yeah, so we know how to calculate a determinant. The determinant of M here is equal to, there's a minus sign there, so it's minus times the determinant of this minor, 1 minus 1, 1 minus t, and then minus the determinant of, because of plus minus, the other minor. I'm sorry, I'm leaving out this row and this column. So I have minus t minus 1, 0 minus t. Always jeopardy. Calculations as complicated as this. So let's see if it works out. So we have minus, and we have minus t plus 1 minus t squared. So that's equal to plus minus t plus 1 plus t squared, which is equal to t squared minus t plus 1, and I breathe a sigh of relief because, as we said, that's the Alexander polynomial of the trephine math. So that's how Alexander defined it. Now, there's a whole story behind this, some of which is in his paper and some of which isn't. He started with a different presentation of the fundamental group called the Dane presentation. In the Dane presentation, instead of wrapping around an arc in the diagram to get the element, what you do is you have a base point out here and you run a line down through the dot diagram, through the region. Then you go under the diagram until you're out in the unbounded region and you come back to where you were. So you sew through specific regions rather than around specific arcs. And then you get a relation in the fundamental group that looks like A, B, inverse, C, D, inverse. Slips off the diagram, okay? And then this is an algebraic reflection of that in a module, similar to what we did before. So that may give you a partial idea of how he got to this. And then he decided, probably because it was made everything as clear as possible, to prove directly that this would be invariant under the Rademacher rules. So if you get that paper, I can put it in our reference list. You will see that the paper begins with a definition like this, and then it does some linear algebra with the matrices, checking that everything is invariant under the Rademacher. You could do it in a linear algebra course. You could give it as a big exercise in linear algebra course. So it's very elementary. But there's more to be seen. I think he had another intuition, which he maybe didn't articulate, that it would be good to look at it this way, even though it's very elementary and doesn't use the group theory. And here's the thing. what is a determinant? Suppose I said to you, find me the determinant of A, B, C, D, E, F, G, H, K. I decided to talk about this a little bit today, okay? But I don't want to go too far with it because not one thing I want to talk about. Yeah. So if you calculated a 3x3 determinant, there's a pattern to it, right? You might know it this way. You take the product of these three, you take the product of these three, you take the product of these three. You take the negative product of these three, the negative product of these three, and the negative product of these three, and add them up, right? All 6 terms, right? Maybe you know that algorithm. But another way of putting it is the following, that you have a grid, n by n grid, and you consider things on the grid that look like rooks that are attacking nobody at all. You have a choice of rooks. Rooks move horizontally and vertically, and these rooks don't attack each other at all, right? And you look at all rook patterns on the n by n board, and each one has a sign associated to it because it's a permutation. So if you look at it that way, then you see you have 1, 2, 3, 1, 2, 3. And this is the permutation. 1 goes to 1, 2 goes to 3, 3 goes to 2. 1, 2, 3. 1 goes to 1, 2 goes to 3, 3 goes to 2. The sign of that permutation is -1. The number of transpositions involved in the permutation. You take the determinant is the sum over the rook patterns of the products of the elements on which the rooks are sitting, multiplied by the sign of the permutation. That's the general definition of a determinant. Well understood for combinatorics that way. So then we can compare with the knot diagram. Suppose I take a term in this determinant, like this term here, right? And I go back to the knot diagram. Let me draw it a little larger. Take the regions A. Leave the dots in. So now take that term in the determinant C is choosing 1. I could think of it that way, or 1 is choosing C. So here's 1, here's 2, and here's 3. And 1 chose C. I'll put a little mark right there that indicates that 1 chose C. And 2 chose E. And 3 chose D. And A and B are not chosen because they're out of the picture. So if I were to draw that all by itself, you would see what kind of a thing it is. A and B are not chosen. First crossing chose this region. Second crossing chose this region. And the last crossing chose this region. And this is a kind of not diagrammatic version of the rooks on the chessboard, where the rooks are these little markers on the diagram. So this rook is not diagrammatic rook is occupying the 1 chooses C. This one is occupying the 2 chooses E, and this one is occupying the 3 chooses D. And what does it mean that the rooks don't attack one another? In the knot diagram, it means that these not diagrammatic rooks have their own regions. No 2 markers occur in the same region. If 2 markers occurred in the same region, that would be bad, but it doesn't happen because every region is uniquely chosen by one of the crossings. So then I have some number of configurations of the diagram that correspond to the terms of the determinant. We found that the value here was a -1. The value here was also a -1, and the value here was a -t. And that came from these dots or absences of dots. Okay, so you see that instead of computing the determinant, I could take a sum over all diagrammatic rook patterns like this, and I would take the product of the values of the module that are occurring with respect to his idea, right? So when you're looking here, you would see a t. When you're looking here, you would see a -t. When you're looking here, you would see a 1. And when you're looking here, you would see a -1. And so if there's a marker here, it will choose a -t. If there's a marker here, it will choose a 1, and so on. Okay? So that's the story, and let's go to the next board and see what that would look like. I'm going to tell you a secret. We can throw away minus signs in Alexander's module formula. And use TA plus TB plus C plus D for this. Now, of course, if you got used to using the minus signs, you might not want to bother throwing them away. But for purposes of describing it to you, it's easier. Because now I say to you, you can just look at the original diagram, and if there's a dot there, then that will give you a T. And if there's no dot, it'll give you a 1, right? And now we want to see how this will work. So we start with the Trephon knot, appropriately dotted by Alexander. And to find the dots, you better orient the diagram so you know what's left on an undercrossing line. So yeah, there's our knot. And then we're going to have actually only 3 terms here. Of course, it doesn't matter, it turns out, which 2 adjacent regions you remove. That's proved by Alexander also, if you look at this paper. But now we're trying to put down diagrammatic rooks that don't attack one another. Every region has to have 1 marker, no more than 1, and all the remaining regions have to have markers. So here's 1. And here's another. And here's the 3rd. Now, of course, there's some pattern to this part of combinatorics, and I want to talk about that in a moment, but this is, so far, those are just the possible terms in the determinant that could be non-zero, right? And now we know exactly what they contribute, except for the sign, right? So we're going to get, these are the states, and we're going to get a formula like this. State 1, sorry, first state, second state, third state, okay. But we're going to get the Alexander polynomial of T is equal to sum over these states, Alexander states. Yes, and I'm not counting loops anymore. This is just equal to the product of P corresponding to a dot, one corresponding to no dot on the state. And of course, dot or no dot depends on the knot diagram that you were working with. So what is the contribution? And then times the sign of the state. And the sign of the state at this point is referred to the checkerboard. But new rule sign of the state is equal to -1 the number of state markers that look like this. In between two incoming lines. I called them black holes for fun. Okay? -1 of the number of black holes in the state. So what is the sign of this state? Well, we have to orient the state. It becomes a purely combinatorial formula in terms of the diagram. It turns out that that sign, and I just told you that's combinatorial in terms of state, changes exactly the same way that the permutation signs do in the determinant. That's a miracle, and it's a little tricky to prove, but this is a nice rule, so just take it for what it is. Let's look here. How many black holes are there in this state? Exactly 1. So this is going to be minus, and then this marker is on a 1, and this marker is on a 1, and this marker is on a dot. Let's look at this one. 2 black holes, so we get -1 squared. And then we get this marker is on a 1, this marker is on a dot, that marker is on a dot, t squared. And this one, we have a white hole, and neither, so that's a plus. And we have 1, and a 1, a 1. So we get t squared minus t plus 1 in this case. And you know that's the Alexander polynomial of Khovanov. Okay, so that's the state sum for the Alexander polynomial. Similar in its form to the state sum for the bracket, but a bit more complicated. It has some bells and whistles in it. There are these states which involve occupancy by markers, and then the other part is like the A and the A inverse in the bracket, where you can tell whether what will contribute by looking at locally at the crossing, and dots in this case cause it to contribute a T, and the sign is given by the parity of the number of black holes in the state. That's a completely combinatorial story for the Alexander polynomial. Okay, you can have some fun with that. Now then, the relation with Conway is to change the marker pattern, the marker structure, not the marker structure of the states, but the following. I should say the weight structure, the polynomial weight structure. What we had here was T1, right? Here's what we're going to use if we want a Conway. We're going to have S minus S inverse 1, 1. And we're going to have for a negative crossing S inverse minus S 1 and 1. And the Conway polynomial is going to be equal to the sum over these states of Ks sine of the state. Oh, actually, the way I'm telling it, I'll leave it this way so we do it in exact parallel. No, those minus signs were going to be the black hole putting inside, but I'll leave it out like that. So you have S minus S inverse, or you have S inverse S. And then the Z is equal to S minus S inverse. And if you play around with that, you'll see that you get exactly the Conway polynomial. And then from there, if you do some further playing around, you will see that you can see why it's related to the Alexander polynomial according to my story, because Alexander is given by this weight assignment, T1, right? And Conway is given by this weight assignment, which is a little different, but you can see that that's a little closer to comparing what would happen if I switched the crossing. And then you can finish the job and prove the Conway theorem. And you can do all the things you wanted to do more easily than you would with the linear algebra, but there's still some combinatorics to work with. You want to prove that this is invariant under Reidemeister moves up to equal dot. You want to prove that this is invariant under Reidemeister moves on the dot, and all that can be done by looking at the combinatorics with regard to the states. So that's the state form for the Conway polynomial and the Alexander polynomial. No, there's a number of things that one could go on and talk about here. One of them has to do with recent work of myself and Nestle Heim. But Nesleon and I realized that this state sum can be generalized to work for natoids, and that it can also be generalized in other ways to work for classical knots. And so there's really a lot more that you can get out of this than just the Conway polynomial. I won't go into that here, except to mention the idea of a natoid. The idea of a natoid is worth mentioning on another board. I'll just write natoid here and say something about natoid at the moment. Natoids, and it's a very interesting generalization of knot theory. But stay here for a moment. There's an exercise you can do with these three states that shows something that works in general. Suppose that you took the state and you smoothed it by using the marker as the direction for smoothing, okay? You could do that. At every marker, it's possible to smooth like that. Marker smoothing. So draw the pictures. That's not an accident. The marker states are in one-to-one correspondence with walks on the diagram that never cross at a crossing and use the whole diagram. An old pencil tracing puzzle, going back to Lewis Carroll. It really does. Somebody gives you a knot diagram or something like that with fourfold crossings, and you're asked to put your pencil down on the diagram and start walking on the diagram. And when you hit a crossing, you have to go left or right. You're not allowed to cross, and you must go through every edge in the diagram once, left to where you started. Okay, an old puzzle. And this polynomial way of thinking of the state sum is a sum over all solutions to that puzzle. Okay, so that's true. I'm not proving it today. Okay, but let's look at another example so we can see it in a more complex example. Suppose that I have this example. And okay. And now let's suppose that I had in mind to do such a thing. I wanted to make such a traverse. Well, one way to solve it is to just go up to it and say, I think I'm going to make a choice here. I'll make a choice here. I'm going to make choices at each one of these. And I want to make the choice in such a way that the thing is, that the diagram remains connected. So I'll just make it, oops. I was doing this the other day with you, wasn't I? I'll make this choice this way, and then I'll make this choice this way. And, what about this one? Now, this one, if I choose it this way, it'll become disconnected. So I should have to choose it that way. I'm not traversing, I'm just making choices. I think I'll do that one this way. And I think I'll do this one this way. And now this one is forced on me this way. And I have a traverse. So you can see that you can solve it in lots of different ways by just maintaining connectivity all the while you're making choices. And then if you walk along it, you will be solving it. Now you choose two base points that corresponded to adjacent regions, and you can find out how to put in the markers by walking from one of these routes. And every time you go through a door, you have to put down a marker. I'll put it black. And you get a tree-like structure there. And you walk from the other route, go through doors, and you get tree-like structure there. You get two trees. And those two trees tell you where to put the markers. You walk away from the route, and every time you go through a site, you put down a marker. See? And now if I walked over to this diagram and I put these markers down, there, here, this one. Then I end up with the marker state. So what we're seeing here is that marker states are in one-to-one correspondence with connected trails, connected Jordan trails. I say a Jordan trail because it's a Jordan curve in the plane and it's a connected Jordan trail, Jordan curve that traverses the diagram. And they're also in one-to-one correspondence with trees, maximal trees on a checkerboard graph. That's what I've been exemplifying. We got two trees. And where are those trees? Go back to the knot diagram again. And you see that one of the trees is on this graph. And the blue tree is on the other graph, right? They're two graphs. They're dual to one another in that sense. And these two graphs each get a tree. If you put a tree on one graph, you automatically are getting the tree on the other graph. So you need these two trees, the two trees together. But if you just had one tree, you would get the other tree. So for example, suppose that I fix my attention on the tree that I'm getting in this graph, which I'm putting on different color now, which went like this and like that, right? There's the tree on the yellow graph. But once I have the tree on the yellow graph, I get the other one for free. Let me draw it black by starting from the root here. And I'm going to let myself go through anything that I didn't go through before. So I go through here because there's nobody going through it. And I go through here and there's nobody going through it. And I go through here. And you see, by complementation in that way, I have one tree determining the other tree. So that says that the trees on the checkerboard graph are in one-to-one correspondence with our states, and the Jordan trails are in one-to-one correspondence with our states are in one-to-one correspondence with the terms in Alexander's determinant. But you see, that tells you that some value for evaluating this polynomial is going to count the number of trees. If I have a state sum that is summing over trees, these are the same as the trees, and I'm putting down some little polynomial for each state. If that little polynomial was equal to 1, then I would count the number of states, and that's the number of trees. And now let's see what's happening with the Alexander polynomial. We could put a 1. If we put a 1, there would still be the sign of the state because I forgot about that. If you put a 1, then you would be getting plus or minus on all of these because of the sign of the state, right? So it won't always count the number of trees. But the fact is, and now we're down to getting near to the proof, but I'm not going to do the proof. The fact is that if K is alternating, and we use P equal to -1, then the Ks, which is just going to be equal to -1 to something, multiplied by the sine of S, will all be same up to a global constant. And that implies, that requires proof, and that implies that the absolute value of the Alexander polynomial at -1 equal to the number of trees. The number of maximal trees. So that's an outline of the proof of what I had told you a while back, that the total number of trees in the checkerboard graph is equal to the modulus, which is the Alexander polynomial at -1. So I'm skipping some steps here, but I wanted to give you an idea of where it lay and how it happened, that the trees would be related to such a thing. And from this point of view, it's because you are summing over those trees. And so under certain circumstances, and one circumstance is alternating not, you actually count the number of trees as a topological invariant of the bond. So you might be curious enough to want to know how to fill in the details there. And that's a nice topic for further discussion. So with that, I'm still not quite leaving Alexander, because there's one other version of Alexander that relates to our next topic. Alexander polynomial can also be obtained from a surface whose boundary is K. And for the purpose of illustrating this, I'm going to draw a surface that's easy to look at, but may not be obviously giving your boundary the trefoil knot. However, I assert that the surface that I'm now drawing has boundary of trefoil. And I claim that the boundary of F is equivalent to a trefoil. Certainly, probably not a boundary. This is not supposed to be a discontinuity there. But I leave it to you to try drawing a picture of that and seeing that you get a trefoil knot. To do that, just put the undercrossing lines back in where I didn't draw them, and play with it and simplify it, and you'll find a trefoil knot in there. Okay, but I've drawn it as a disk with attached bands that have some curling in them, and then the way this happens is as follows. You look at a fundamental collection of curves on the surface. I'm going to draw them and then say why I regard them as fundamental. orient and name without names. Now, this is a surface of boundary, and um, and and these two curves contain most of the topology of the surface. If you think of a bit of band like this, and a curve going down through the middle of the band, then the band can be projected down to just the curve itself by retraction. Just push everybody along those lines there down, and you end up retracting to the curve itself. In a similar way, the surface can be contracted until the surface really turns into, and it can be seen as a neighborhood of these two curves that are intersecting. So you have these two curves, and they intersect one another at a point. So topologically, they're just two circles that touch at a point. But the surface can be thought of as a neighborhood of them, that you've expanded a bit of surface around them and produced this. So, in fact, I could show you what I mean by that idea of a neighborhood by making a neighborhood of these. Suppose I drew just these, and then I start walking along, and I have the effect of thickening the curves by walking along a curve next to them, like this. And I keep on doing that until I come back to where I started. And I am producing the surface as a little neighborhood of the skeletal curves that are touching like that. So you can in fact, whenever you have a surface with boundary like that in three-dimensional space, there's a fundamental system of curves that to which the surface retracts. And you take such a fundamental system of curves, and then what you do is you look at for any two curves, curves alpha and beta, define theta of alpha beta to the linking number of alpha star beta, where alpha star is equal to alpha pushed off the surface by a small amount in the positive normal direction. Okay, so then we would get a matrix with regard to this. Let's take A and B and see how this will look if we measure it this way. The way this happens, of course, depends on the knot itself, depends on the boundary, and it depends on the surface. Depends fully on the surface. If I take A and I push it, and let's suppose the positive normal is out of this is the normal direction, like that, like that. So, so I push A upward a little bit, and it's no longer intersecting B, but it's going around B now, and it's got a positive linking number. So A would be as a 1. On the other hand, if I push B up, I get 0 because now B is floating above A completely. I get a 0 linking number. And then there's a little bit more complex thing that you're going to have to look for to find out what happened here. We're orienting this. And you want to know what happens when you when you push the curve itself off itself and watch how it links with it with its previous owner, right? Take the red curve and push it up a little bit and see what happens to it in relation to the red curve. Well, you're going to have to visualize a bit. And I'm just going to tell you the answer. The answer is that you just look at the crossings of the curve with itself in this projection picture. And you take the sum of their values. See, that's a -1. That's a -1 sign. And that -1 sign and the other, there's a -1 sign for that one. Those are in fact the self-linking numbers that occur here when you do that. You need to stare at it a bit to see that that works, but it does. You're going to take this curve and you're going to push it off itself so it goes perpendicularly and forms a little perpendicular strip with regard to itself. And then you want the linking number of that with itself. But it's a perpendicular strip. And if you just turned it by 90 degrees, you would see the strip. It's right there in front of you. So the linking number between these these curves on the edge of the perpendicular strip is the same as the linking number between the curves on the edge of this flattened strip. So the self-linking number. I may be confusing you, but I tell you, you will see that that's true if you try it. And then there's one further thing that you need to be apprised of, and that is that if you have somebody like this, and then if you stretch it out, it turns into a 360-degree twist. So every time you see one of these, it corresponds to one 360-degree twist. So that's the basic thing about the self-linking. And this fact about the self-linking occurs again and again in applications, which is one of the reasons why I wanted to bring this up. You see, if you have a belt and you put a 360-degree twist in the belt and you relax the belt, then it becomes parallel edges like this in a little curl. And if you have a little curl and you pull it, it becomes a 360-degree twist. So what happens to the self-linking when you represent a surface in this way is you can count the amount of writhing in the curves, and that will be their self-linking. And then you look at the linking numbers between them by pushing them off. You get this matrix. This is called the Seifert matrix. And the Alexander polynomial turns out to be equal dot to the determinant of the Seifert matrix minus T times the transpose of the Seifert matrix. Amazing. Another point of view entirely. And of course, in order for me to prove that relationship, I'd have to go in a different direction and tell you more topology than we have time for. But nevertheless, you should see the exercise done, right? So we can do that. Here's our Seifert matrix, -1, 1, 0, -1. And we want to take the Seifert matrix minus T times the transpose Seifert matrix. So that's going to be -1, 1, 0, -1, minus T times -1, -1, 1, 0. That's a transpose. Then writing that out as a single matrix, I have -1 plus T, 1, 0, 0 minus T, and -1 plus T. If I take the determinant of theta minus T theta transpose. I get -1 plus t squared plus t plus t squared minus 2t plus 1 plus t is t squared minus t plus 1, our old friend. Okay? Works. And Conway of S minus S inverse, or T, turns out to be equal to the determinant of S theta S theta minus S inverse theta transpose. Between those two, Conway's theorem is very apparent. Because it's just the change of variable and playing with determinant will get you Conway's theorem about the relationship between the two. But when you write it this way, it turns out that it's invariant without any equals dot. It satisfies that nice identity and so on. So this is one of the nicer reformulations of the Alexander polynomial because it shows you that you can understand it geometrically in terms of these surfaces whose boundary is the polynomial, and that it's just coming from linking numbers. And then if somebody said to you, well, I'd like a Alexander polynomial to be such and such, then you think, oh, I could make a surface with the linking numbers this way and get you your polynomial. For example, could you give me a non-trivial knot with a trivial Alexander polynomial? Well, what would a trivial Alexander polynomial look like? You could draw a trivial knot. Here's a trivial knot. The boundary of that is the unknown. Do that and do that, pull it apart. It's an unknown, right? So that surface, without any twisting or anything in it, it's just an unknown surface. But you could work out, when you see how the Seifert pairing then, the Seifert pairing is extremely simple and it will calculate out to give you a trivial Alexander polynomial for sure. Won't be any problem. But then you see that you could make some other things that would still give you very simple Alexander polynomials, like putting twist in one of these and no twist in the other, and it's still an unknown, right? So then you can play games. I don't want to do more examples right now, but you can play games with this. You can produce lots of knots with Alexander polynomial 1. Conway polynomial 1, they're non-trivial. You have a direct geometric pathway into understanding how the polynomial behaves. And this is what we do not have for the bracket polynomial or the Jones polynomial or any of those others. We don't have some kind of nice, interesting topological picture behind what's going on that shows us something that would let us design a lot of examples. All right. Okay. So now, let me go back to bracket. So we have that the bracket is equal to the sum over bracket states. of the product of the weights, which are A and A inverse, times D to the number of loops. We'll leave it unnormalized. A number of loops minus one, but maybe I'll figure out one. For today, let's have that the bracket of this is equal to D, but D is equal to minus A squared minus A to the minus 2, and bracket of this is equal to A times bracket of that plus A inverse bracket of this. So I haven't divided by D on value. So now, that means if you were to write it out, that it isn't quite as beautiful as you might have liked it to be. It's going to be A to the number of A smoothings minus the number of B smoothings, right? That's the A inverse. And then we're going to have minus A squared minus A to the minus 2 to the number of loops in state. That's what the formula actually is. But one thing that we could try to think about is what would a formula look like if I could write it as a sum of monomials so I could understand it better, understand the polynomial better, right? That makes sense. Well, here's a way to do that. Idea for enhanced states. Zero. Idea, but that's a lot of nice consequences. For each loop in the state, I'm going to put a plus sign or a minus sign. Okay. And the evaluation of the plus is going to be equal to minus A squared. And the evaluation of the minus is going to be equal to minus A minus 2. And then we sum over the larger collection of states with signs. So for example, the evaluation of this is the evaluation of a plus the evaluation of a minus, because we sum over all the different sign versions of a loop. And then this will be equal to minus A squared minus A to the minus 2. So in other words, what I want to do is I want to push the binomial theorem into the combinatorics. Now notice how this will work. What will happen if I had two states? Then I'm going to get the sum of that, of course, is going to be let's call this alpha. This then is alpha inverse. And then the D is alpha plus alpha inverse. So then I'm going to get alpha squared plus 1 plus 1 plus alpha to the minus 2. And that, of course, is exactly alpha plus alpha inverse squared. So it's going to work exactly right. And instead of having to put in the power to the number of loops, I can forget about counting loops altogether. I just have to count how many loops have plus, how many have minus. That I still have to think about. And I'll get a new formula for my new state sum. So my new state sum equal to the sum over S enhanced. And now how can we say it? How can we say it? We're still going to get A to the number of A minus the number of B states, right? A states, B states, A smoothing, B smoothing. Now, how many you get? But that's not all. Then I also, for each loop, I either get alpha or alpha inverse. So I get times alpha to, and I left out the signs completely this way. That's good. Now, the signs are coming from the alphas. I get alpha to the, what I'll call lambda plus minus lambda minus, where lambda plus is equal to the number of loops that are plus, and lambda minus is equal to the number of loops that are minus. And now I have a sum of monomials, which we can write out in a little more detail, right? Let's finish by writing that out in a little more detail. Okay. So we have that bracket K is equal to the sum over the enhanced states of A to the, let me try, number of A of S minus number of B of S times alpha minus A squared to lambda plus of S minus lambda minus of S. Where lambda plus of S is the number of plus signs in the state, and lambda minus is the number of minus signs in the state. So what would that look like if you were looking at some state? You might have some state like this. Maybe that's an A smoothing, and this is an A inverse smoothing, and that's an A smoothing. This is plus, and that's plus, and this is plus. So then this is going to contribute A times A inverse times A times alpha, the value of a loop, to plus 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 to the third power. And then that's going to actually be A times minus A squared cubed, which is going to be equal to minus A to the 7th. So it's a monomial. And if we wanted to write it all out as an exact monomial here, it will be the sum over S of A to the number of A minus the number of B times. We could just abbreviate this as lambda of S times minus 1, minus 1 lambda of S, and A to the twice this, so that's A to the 2 lambda of S. So that's plus 2 lambda of S. And so now we have it. Now we have it written out as a sum of monomials. polynomials like that. So if you were wondering, for example, what is the coefficient of a given power of A, then you can think about what that means by dividing it up into those states that have that power, right? So, let me see what I want to say. Let's call this J of S. So just looking at it that way, then it's sum over the states of A to a certain function of the state, J of S, times -1 to another function of the state, lambda of S. And you could ask, well, is the coefficient of a given power of A 0 or non-zero? What is the coefficient of a given power of A? I'm trying to think of the polynomial without, going into the details of the link, but on the other hand, I'd like an exact formula. So I could rewrite this as the sum on J of A to the J times whatever will contribute to a given J. So this is going to be the sum on states such that J of S is equal to this J, this fixed J. And then what do I get? I get -1 to the lambda of S. Now, I think that will, yeah, but then you have to say what you meant here. So then you're given that fixed J, you chose it, like 5. And then you ask, well, which states have that the number of A's in that state minus the number of B's in that state plus 2 times the number of pluses in that state minus twice the number of minuses in that state, right? End up having J as that number. But you see that involves states all across the board, various states. And you would have to then look at all the states and think about and check which ones have that number. You have to go across the entire collection of states, find out which ones have that number, and then add up the signs of them accordingly, and that will be the coefficient of the A to the J. So this is not simple. It's not an easy matter to determine whether a given monomial has a non-zero coefficient or not. And up to normalization of the polynomial, these coefficients are invariants of the knot. But by the time we've expressed the combinatorics all the way down into that, it has become somewhat opaque as to what's going on. So we're faced with this question. I don't want to go over, and I'm already over it. Yes, we're faced with this question. How do you think about the structure of the states and understand how the invariant is affected by the structure of its states? And you could continue in this vein without doing anything higher level. You could keep on working with the combinatorics of it. Some people have. But another thing that happened, partly because of this kind of frustration, was was an idea due to Khovanov. And I'll talk about it next time, one lecture rather than I thought I would tell more, but one lecture. And Khovanov's idea is to view the states or the enhanced states, but it doesn't have to be just the original states first as a category. That's not such a highfalutin idea at first. It's actually a very simple idea. Consider, for example, the states of the Hoffman, right? So we have the A state of the Hoffman. And then I could smooth one of them or the other one, make it into a B, if I could manage to. Oh, so I'm going to take this A and I'm going to turn it into a B. And I'll leave this one an A. I'm going to take this A and turn it into a B. Leave this one an A. Or I'm going to take them both and turn them into B's. And there are all the states of flame. But I've done an organizational notion. I start with an A and I put an arrow going to the state that has now a B. So that means that an arrow between two states, a single arrow between two states means that one A was changed to one B. And of course, by changing one A to one B, one at a time, I generate all the states and I get a cubical structure. In this case, formally, an A, formally, I get an AA, get an BA, get an AB, and I get an BB. And this generates a little category. A category is just a very general mathematical structure. A category is a structure that has nodes or objects and morphisms or arrows between objects. Hence, it's a directed graph, like this is a directed graph. But in the category, if you have an arrow from A to B and an arrow from B to C, then it's given that you have another composite arrow from B to C, which you don't necessarily draw when you're drawing everything in a category. So in this case, for example, we're starting with this and saying it's a category. And in order for it to actually be a category, I have to add something because of the definition of the category says there are compositions. So there has to be, I was going to choose a nice color like red or something. There has to be compositions. So we have this composition. And then there is also an identity arrow at every object like this. Well, now I've drawn a directed graph that actually could be a category if these arrows commuted, that doing this is the same as doing that. And in general, there might be another arrow here for this one, which might not be the same as that one. It all depends. Okay. But that's all a category is just a directed graph such that when you compose arrows, you still have another edge in the graph, and identity arrows, which don't change anything under composition, and that arrow composition is associative. That's a category. So Khovanov says, well, why don't you look at it as a category? Then it has this structure. This category, so they all will look like cubes of different dimensions. If you have two crossings, you'll have a two-dimensional cube. If you have three crossings, you'll have a three-dimensional cube category, and so on. If you have an n-cube category associated to a graph, associated to a knot diagram, and the states are forming this n-cube category, and then Khovanov's idea. Well, the pre-idea is how to measure category to get topological information about the knot. That's the question, right? So suddenly I'm throwing away the idea of not polynomial and any of that. I'm just looking at the states and I'm saying, here are the states. They're organized at least in this way as a category. And if I did a Reidemeister move, they would all change together. Not all of them, but some of them would be changing. Some of them would not be changing, maybe. And I want to look at how the states behave, how the whole collection of states behave, how the whole category behaves as I move the knot around. And how can I measure that? And Khovanov's answer is homology of the category. It's unappropriate. Now, you may not even know about homology, or maybe you do. But I'm at the end of my talk, so I have to tell you about that next time. But the thing I need to tell you about right now for you to think about in between is that a category, if you think about it abstractly and concretely at the same time, actually looks like a space, whatever category it is, any category. All categories look like spaces made out of simplices attached to one another. It's just a fact of life. Because of the following, suppose you had two arrows and you connected them together. Then category says there's a third arrow. So that says that two arrows in sequence actually correspond to a two-dimensional simplex. And one arrow all by itself is a one simplex, of course. What about three? And then we'll stop. I want to convince you that a sequence of arrows in a category should really be thought of as a simplex. Well, given these two, there's a morphism that connects them, right? Given these two, there's an arrow that connects them. And then given these two, there is the composite arrow, this one, that one that connects this one. But by associativity, that's the same as this one, that one. So this arrow is the same arrow, however you want to think about it. And now look what I drew. I drew a picture of a three-dimensional simplex. And if you had four arrows in sequence, then they give you a four-dimensional simplex. The category gives you, for every composite of arrows, it gives you a simplex of that dimension. So that if you think about the compositionality that the category is talking about, then it's a big space. And the single arrows are one simplices, two arrow compositions are two simplices, three arrow compositions are three simplices, and on it goes, giving you a big space, and they're all pasted together in a certain way. And that is how you can think of the category as some kind of big space, and then you can measure the properties of that space. And that's what's meant by homology, is a way of measuring the way simplices and things like that fit together. But we have to stop now, and we'll see how much we do on Friday, but I'll try to give you a general picture of how this approach works and how it does begin to give us some understanding of the states globally.